going to discuss discrete random variables. So in the last lecture we introduced the notion of the random variable and how that abstraction is better than dealing the even space, and we basically told that it is nothing but a function, real valued function mapping from the sample space to the real axis. And then we also mentioned how we can characterize this random variable using the cumulative distribution function and either the probability mass function or the probability density function as based on the fact whether it is a discrete or a continuous valued random. So with this, and we also looked at the properties of those PMF and CD. So it's a real valued function mapping from S to R. This is one thing that we looked at, and then we looked at the probability mass function or the probability density function and the cumulative distribution function. We looked at the CDF. Okay, we always use the capital letter for the random variables, small case letter for its realizations, and then we use the symbol probability that x equal to x, like that for the probability mass function. This is how we will write the PMF for all possible values it can take in its range. That is, if x is the random variable, we can call Sx as its range. This is different from the sample space. Okay, as the range means the set of values it can take, or the range in real axis where its values are allowed. And in the case of the probability density function, we use the notation small fx of x. For the case of the cumulative distribution function, we use capital Fx of x. Okay. And then we looked at some of the properties of fx of x, that is fx of minus infinity is equal to 0. This is one thing, and monotone, non-decreasing function, CDF, and then they have a relationship, fx of x is equal to probability that x is less than or equal to x, and we can obtain it later on. We will see from how they are related to PMF or PDF. In the case of PMF, it is the summation of all the values, okay, all values I element of Sx, I less than x, probability that x equal to x. So you look at, you are evaluating at x, so you look at all values I which are in the range of x, but less than x, you sum all those probabilities, you will get the CDF. So similarly, you can relate the PDF and CDF for continuous value random variable. Okay. PDF is the differential of the CDF, and you can get CDF to an integral. We will see later on. Now we have restricted ourselves to the discrete value random variable. You can take countable, finite, or countable infinite values only. So what we will do is we will look at some of the familiar discrete valued random variables that we will encounter in nature. The first one is the so-called Bernoulli random. So this is a random variable which can take only two possible values. It corresponds to those random experiments where the outcome can be classified into only two categories. We may call it sometime as success or failure, head or tail, and so on. So only the corresponding random experiment has only two possible outcomes. So the even space will have only two outcomes. We may call one as the success, let's say yes, another as failure, or F. Then we may say that even space as yes, F, S comma F. So this is the sigma algebra. Of course, we will, once we go to random variable, we won't be later on be looking at the even space, but to just give a connection, this is the kind of random experiment and sample space on which Bernoulli random variables are different. Only two possible outcomes. So one more thing we have already seen is the coin toss, which gives rise to only two events, head or tail. Or you ask a question which can have an answer yes or no. Okay, or it can be an you test an equipment, okay, a product. It can be accept or reject. So these are some of the random experiments where there are only two possible outcomes. You ask the question, the answer can be yes or no, not any other descriptive answer. Or you have a product which have to be either accepted or rejected by getting into a test, or it can be a pathology result whether there is a disease or not, okay, and so on. So such random experiments, if we have, we can define Bernoulli random. So what we will do is, so what the events or success or failure, so we have to associate a real number to it. That's what basically a random variable is. You can associate any distinct real number, no problem, whatever it is, +1, -1, and then -156, and then 2,535,000, anything you can, as long as it is distinct. By convention, we give 1 and 0. When there is a success, the random variable takes a value 1. When there is a failure, it takes a value 0. Then let x is the symbol we use to denote a Bernoulli random. So, and x is Bernoulli. Then probability that x equal to 1 is the same as the probability that success occurs in the random experiment. We will call the success probability as P, and probability that x equal to 0 is probability that failure occurs, and that is equal to, we will call it as Q, it should be equal to 1 minus 1. So we will say that a Bernoulli random variable can take only two values, 1 or 0, 1 with the probability P and 0 with the probability 1 minus 1. That completely defines the Bernoulli random variable. So whenever we talk about Bernoulli random variable, we may say x is Bernoulli, or y is Bernoulli, p is Bernoulli, and so on. We have a shorthand notation of using x, this kind of a tilde, b or n, or you write Bernoulli, whatever it is. And it is enough if you give the success probability. If you know the success probability, failure probability is known. You also know that success and failure are only two possible, one, and by convention, the random variable takes a value 1 or 0 depending upon whether there is a success. Everything else is fixed. So it is enough if you tell that X is Bernoulli with probability with parameter P, which is the success probability. So when we use this kind of a notation, then it's automatically understood that it's a Bernoulli random variable. Everything else is follows from it. Then how will the PMF for Bernoulli random variable will look like? There are only two possible values it can take. So it takes a value 0 with a probability Q and 1 with a probability P. That can be different. So how will the cumulative distribution function look like? What is it? Probability that X is less than or equal to X. And this you can find it for any X, minus 15 or plus 100, whatever it is. So what you have to do is you take any X and you find all values that are in the range lesser than that. You add all probabilities starting from minus infinity up to this X, and that is the value of the cumulative CDF of that. So up to 0 there is no value it takes, and if you add all those probabilities it will be 0. So it takes 0 only up to the CDF value is 0 till the first value, realizable value 0, that you enter. After 0, between 1, the only value it can take is 0, whose probability is Q. So it suddenly jumps to Q. At 1, okay, and after 1, then what happens is that the probability that X is less than or equal to 0 means probability X equal to 0 plus probability X equal to 1. And that becomes equal to 1. So it again jumps by value of P and becomes equal to 1. So this is how the CDF works. CDF will always, for discrete value data variable, CDF is always star-based function. Well, now we will talk about the next random variable, which is a binomial. There are two a random variable which is very related to the Bernoulli random variable. It is called as the indicator random. What it is just for our convenience we are introducing here. Here, success, failure, head or tail or something that we may associate. Suppose if a random experiment is conducted, many possible events can happen, not just two outcomes. Many events can happen, but there is one particular event on which we are interested. We are only bothered about whether the event has occurred or not. Okay, then we can define an indicator random variable. The sole purpose of this random variable is to indicate whether the event has occurred or not. So then we will call if I is the notation that we use, and then X or something we can use for that. Then, so sorry, if A is the event in which you are interested, and IA stands for the indicator random variable, keeping track of or bookkeeping the occurrence or non-occurrence of the event, then this is the notation that we use. I always means it is an indicator random variable. The event we are interested in is put as the subscript. So again, it behaves like a Bernoulli random variable. It can take only two possible variables, 1 or 0. 1 indicates the event has occurred. And what is the probability? Probability with which the event has occurred, P of A. So you have an event space in which A, B, C, so many events are there. You can always find the probability of A. And that A Okay, that probability is the probability with which 1 is realized. 1 minus PA is the probability with which 0 is. So, here A is nothing but our success in the Bernoulli. So, this is the indicator random variable. There is one more trivial random variable which can get rid of it. Constant random variable. That is, it takes a value, a constant value all the time. Okay? It is not only deterministic, but it takes a given value. So here x is such random variable. Then probability that x equal to c for some constant value is equal to 1, and probability that x not equal to c is 0. So if you want, we can also treat sometime a constant also as a random variable. It's very trivial. The next one we are interested in called as the binomial. Here what we do is we do a sequence of Bernoulli trials. Is it visible to people in the last benches, or should I increase the font size, or you can just please whether you are audible or whether what I write is it are able to is it legible, you can always tell me, I will accordingly change. So you do a sequence of Bernoulli trials. Let us say we do n to be for concreteness, we do n trials. But the nature of the Bernoulli trial is that each trial is independent of the other trial. For example, if you toss a coin, what you get in one toss will have no implication on the outcome of the next toss, which is very correct way of modeling. But it is not necessarily true for all the things. Suppose one person writes a same subject exam many times until he wants to get some mark more than 95 or so. He repeats the same exam, GRE or whatever. So they are not independent. Okay. The second exam, second attempt are supposed to give better mark. So it's not like that. These are all those kind of random experimental trials in which each trial are independent from the outcomes of the other trials. So for such cases, we use the notation IID, which I would like to introduce at this stage, and we will be using this acronym very frequently. It stands for independent, identically distributed. So we usually call this IID random variables very frequently. By that what we mean is the random variables are independent of each other. I am going to formally introduce the notion of independence. We looked at the notion of independence of events. P of A given B is equal to P of A. Similarly, we can tell whether two variables, random variables X and Y, are they independent or not. That we will define using what is called as joint density function, distribution function, marginal and so on. We will come to that later. But I think now itself it should be obvious to be, you will get a feel of what we mean by independent events. Whatever X realizes, that value is not going to affect the realization of Y randomly. That's what we mean by independent. And they are identically distributed. That is, you will have different random variables. Let us say Bernoulli random variable. Let us say we have used the word X for that. So we use sequence of random variables n for X. So in the first one it's a Bernoulli random variable, that is the output. So that we can use it as x1. One for which trial it is. Second is the x2, x3. Xn. So the n trials will give rise to n Bernoulli random variables. We use this notation to represent it. So each Bernoulli random variable is independent of other. That is the value. If you say that I am trying to go a little deeper, which will come later. Probably x1 is equal to x1 and probably x2 is equal to 1 if you ask. Okay. But of course this takes only 1 or 2 possibility, 1 or 0. So this will become like this is equal to this. This condition will have no say. So if you are given a value x1 takes, conditioned by that, how will the value taken by x2 will change? If you ask such question, it is not going to change. That is what we mean. We will come to this point much later. But that I think will give you an idea of independence. Identical in this sense that distribution, which is a general word, what we here means the PMF, CDF are all the same. They don't change. For example, it can change. If I can toss a coin in such a manner that as the first toss it's a fair coin, the next one it's not I am telling the same coin. I am doing coin tossing. I take it from my bag and then take a coin. The next one it may be a weighted one. The success probability, hit probability can be different also. The P itself can be varying from trial to trial. If that is not the case, it is still independent, but they are not identical. So now let's stick to the case that they are all IIDs, independent and identically distributed random. You can have IID Bernoulli random variables, IID Poisson, IID normal, all those things we will talk later. IID random variables. Okay, now the question is, so n trials I conduct, I count the number of successes in n trials. Okay, so what are the values it can take? And this is going to be a random variable. The number of successes vary. If I do once, I may get some value number, other time it can be different. So it's a random variable. I will call that as x. See this x is okay. I will maybe call it as y. Y denotes the number of successes in the n trials. So this is again a random variable. And that is what we are going to call it as the binomial random variable. So what are the values y can be? The range of y. So what are the values? Number of successes in n trials. 1 to n. Or 0 to. There can be no successes or 1 or 2. Or at the maximum there can be only n successes. And nothing beyond that. So that we call it as the binomial random variable. Now you want to characterize it. So these are the values it can take. What is the probability it takes a value to 5 and so on. So first, again we have a shorthand notation for Bernoulli random variable. Similarly for binomial also, we can have a shorthand. Here what we need to tell to completely define a Bernoulli binomial random variable is number of trials you have conducted. We will call it as n. And the success probability, we will call it as 2. That's all you need to tell. Because by definition, binomial random variable consists of a sequence of IID Bernoulli random variables. So Bernoulli random variable has only one parameter, success probability P that you have done. But the number of Bernoulli trials is n. That also you have given. That's all. You have told what the random experiment is all about. There are the random variables also. That you will call it as y. Now what we are interested in is the probability that y takes a given value small y. This is what we are interested in. Okay. Well, instead of using y, I will use k, which is very. This is a small k. This is a capital K. What is the probability that? Sorry. why is not? So here what will happen is, so what does it mean? There are k successes that are occurred. One way it can occur is that if I list out in a given n trial the heads and tails, for example, let me take a case of the coin toss. I can have a head, tail, head, and so on. So I have done n trials. If I count the number of heads, that should be equal to k. If that happens, then the binomial random variable will take a value small k. This is one way in which the number of successes can become k. Well, if this happens, what is the probability with which this sequence of outcomes will come? First, head. Head occurs with the probability small k. Then this is independent of that. So the probability has to be multiplied. Okay, independent means we have to multiply. And then this is q. This is q, p, and so on. It is to get the overall probability that this particular sequence of head and tail occurs, such that there are totally k heads in this and n minus k tails in this. But in this particular order, if you want, so this is how you have to get, and you know that there are k heads and n minus k tails. So this is the probability. And there are many such sequences which will all lead to the case where there are k heads, 1 minus k heads and n minus k1. And how many of them? There are n choose k of them. So this is the probability that the binomial random variable takes the values small k. N choose k, p power k, 1 minus k power n minus k. So this is the binomial random variable. Well, now let's just look at how this will the PM of other thing how can be like that. I will take for the case of n is equal to 10 to get a feel of how this will look like, and p is equal to 0.5. And I think it's a 10 dash whatever it is. If this are the case, and here p is 0.5, incidentally q is also 0.5. There are 10 values, start from 1 or start from 0. And then this goes up to 10, and then so the way it will be like that, the PMF so it will be something like this. It will be symmetrical. That happens because P happens to be 1. Later on we will see that the mean expected value or mean of that is product of these two, which is 5. That is why it is peaking up. On the other hand, if the same n is equal to 10, p is equal to 0.3 if you look at. So it may be something like this. It will peak at 3. If it is 0 point something, it will be skewed and it will be so the binomial random variables PMF can be symmetrical or it may be skewed one way or other. Those things you can find, you figure it out based on the success probability. I think that is okay. We will move on to the next random variable. Geometry geometry kind of. Incidentally, you always have to check that when I say this is the PMF for k is equal to 0, 1, 2, 4, then what you have to do is that is they all should add up to 1, and whether it occurs can be between the p varying 0 to n choose k, c power k, 1 minus p power n minus should be equal to 1. And it happens because this is nothing but a binomial expansion. P is one factor, another factor is 1 minus p and power m, and this is equal to 1 power m, that is equal to 1. So PMF should always add up to 1, which you have to cross check. Coming to the geometric random variable, here what we do is again a sequence of highlighting Bernoulli trials. And now you look for the number of trials you have to perform to get the success for the first one. So that number is a random variable because you may get success immediately in the first trial, or it may be unfortunate you may get it in 10th or 20th or whatever it is. So that is a random variable, and that is what we call as the geometric number. We will again call x as the geometric random variable, and again here, what is the parameter that you have to specify for a geometric number? The only thing that you have to specify to characterize it is the success probability. N is not, you don't even know. N is the number of trials you have to perform. So, this is one way of specifying. Some people may use GOP, which means it's a geometric random variable with success probability. Because it is IID, they are independent, and all the P remains the same for all trials, and so on. So here, how do we characterize it? Which means that what is the probability mass term? That is, what is the probability that x equal to I? Before that, what are the values x can take? That is the number of trials you have to perform to get the success for the first one. It can be 1 or 2 or 3, and it can go to any number. So this is one case of a discrete random variable having totally infinite values. So we are by PMF we are asking for a generic I in this range. What is the probability that the random variable will take that value? If you can find for a generic I means you know for everything, that's all is the probability. It may be if you know that it is the P1 is the probability for 1, P2 is the probability for 2. Giving all this list is what we call as the probability mass. So here if you are asking that probability that the number of trials has to be I, which means only in the ith trial you get success for the first trial. It means there has to be the corresponding event is that there is a failure, and so on, finally success. So for I minus 1 time you get failure, and then the ith time you get a success. And then x will take a value. And again, what is the probability? Q power I minus 1 So this is the way the geometric random variable is. Q power I minus 1 is this. So if I is the value, there are I minus 1 failures followed by a last success. This is how it is. So again, if you want to check whether the PMF adds up to 1. So I will define another random variable. See, I varies from 1 to infinity, I minus 1. So if I minus 1, I call it as k varies from 0 to infinity, 2 power k, and what happens? This is a geometric series, so you will get 3 divided by 1 minus 2, this one. So this is the geometric random. Again, why it is geometric random variable? Because if you look at the PMF, it's a geometric series. Okay, so that is why it is called as the geometric random. The geometric random variable has a very interesting property. That is called as the memoriness property. Suppose you have a random experiment, a generic random experiment, and which you keep trying something. For example, let me take this. You have a law, combination law. You know the actual combination number, but you have forgotten. So you have to try out with what you recall. You tried once, it is not working, tried again, it is not working, and so on. But because you recall to some extent, in the 5th or 6th, 7th try, you may get the success. So the more you eliminate, your success probability will increase. So first you ask, with your knowledge, what is the expected number of times you need to try before you open the law? You may tell that, I think in 10 tries I may be able to open it. Like that. Now you did it 7 times, it is not working. Now you are asking again the same question, what is the remaining number of times you have to try before you open? You may tell, I think we are now in 3 tries I may be able to do it. Because you have eliminated something that helps you in doing the other thing. So in many such cases, the more the number of trials you conduct, okay, the remaining number that you have to perform may reduce. That will help. But in certain kinds of Bernoulli IID random variables, it may not. For example, let us take a coin toss. I am looking for a head. I toss it once, twice, thrice. I am getting only tails. Okay. Before even I toss, I may ask what is the probability that I will get a head in less than or equal to 5 trials. You may be able to compute. Right now also you can do some, you can find it. Okay. Now let's keep conducting trials. For 3 times I only get a tail. The next time asking, with this knowledge, the 3 times tail has come. What is the probability the next time a head will come? That is not going to depend upon how much time I failed. Okay. So the remaining number of trials I have to perform to get a head is not going to depend upon the number of times I keep getting tails. Which means that at any given time, if you are told that the success has not come, only failures have come, what is the remaining number of times I have to conduct to get a success? Is still the same. That is not, it will lose all the memory of how many times you have failed. Because every time the success or failure is equally likely, not equally likely, occurs with some probability. And no matter how many times you have failed, that is not going to improve your success probabilities. So those are the kind of experiment where memory is lost. So that is what is called the memoryless property, and geometric random variable exhibits this property. That is, let X be geometric with a property P. Then what you did is you do K trials and find that success has not been encoded. Then, which means that you have to perform additional trials to get this success. But why? You know the number of additional trials to get success. For the first time, it's always there. Well, y is also a random variable. Initially, x was a random variable before you start conducting. You are conducting, and k trials has only led in failures, and now you stop and then ask the remaining additional number of trials you have to conduct to get this success. That is y, and y is also a random variable, and it is related to x by the fact that x is equal to y plus k, or y is equal to x minus k. Now what you are asking is, if you are to start with, you know what is probability that x equal to y. You tell from that formula it is q power I minus 1. Now this has happened, k failures are happened. Now if you ask what is the probability that x equal to y, that will change. X cannot take a value less than or equal to k, because k failures are already occurred. Can only take values beyond that. That is something you know. Now you are asking what is the probability that y is equal to some value, okay, say I. So given that x is greater than k, so this is what we want to know. Probability that y is equal to I, given that x is greater than k. So it's P of A given B, so it is P of A intersection B. So what is this probability of? I can write x in terms of x. Y is equal to I, x equal to k plus I, and x greater than k divided by probability that x greater than k. Right? If you look at these two conditions, okay, for positive k, positive y, and so on, if you are, this condition implies this. Okay. If x is greater than k, will be satisfied for any I, okay, one or more. Because so it is enough if we retain this condition. This condition will definitely hold good. So we can write it as probability x equal to k plus I, given that probability that x is equal to. So first of all, we will just look at what is probability that x is greater than. It is 1 minus probability x is less than or equal to. That way you can find it out. That is 1 minus probability that x is less than or equal to. And this is the CDF of the geometric random. We have not looked at the CDF, but we can find out that. And what is probability that x is greater than k? How do you find out? One way is to actually find CDF, sum all the way up to the k, and then 1 minus, that is what we want, okay? That way you can find, or from k plus 1 onwards to infinity we sum it up, and then you will get. This value is k plus 1 onwards, you have to sum it up to infinity. Or sum from 1 to k and then 1 minus that to it. But can you give a value for this without doing this? What does it say? X has to be greater than k, which means that the first success should have after k times. That's all. It can happen at k plus 1, k plus 2 any time later, but first success should happen only after k trials, which is another way of telling that the first k trials have to be failures. So it is q into q into q k times. It is equal to q power k. So this is what probability that x equal to k plus I, which means that if you see with the same geometric random variables PMF, we put k plus I. It is q power k plus I minus 1 into p. Right? So what is this one? This and this goes away. It is q power I minus 1 into p. This is what we are getting it for probability of this one. So let me again put it here. What we have got the probability that y is equal to I given that x greater than p is equal to q power I minus 1 into p. Which means that y is also geometric with the same probability p. If y is geometric with probability p, this is what the PMF it will take. P is equal to y equal to, right? So this condition is not altering it. So the number of remaining trials you have to perform to get a success is still a geometric random variable with the same success probability. So this is what we call it as the memoryless probability. Well, there are only two random variables which have this memoryless probability. One, in the case of the discrete random variable, it is the geometric random variable which has the memoryless probability. Later on, in the continuous random variable case, there is an exponential random variable which has this memoryless probability. Only these two random variables have this property. No other random variable has this property. It can also be proved that if we can show that there is a random variable which has this memoryless property, if it is discrete, it has to be geometric. If it is continuous, it has to be exponential. Which means that this should be the PMF for the geometric PMF is the only